Assalamu alaikum everyone. I'm NCTFET. I'm going to present on negative capacitance FETs. The concept of negative capacitance in FET is basically belongs to amplify the internal potential without modification of transport phenomena. If the empirical Moore's law holds forever, then in near future the dissipative power density in a chip will surpass the maximum heat removal limit 1000 watt per centimeter square from an IC by using conventional technology. To reduce the power hunger of IC, the transistors should be designed such that it can turn on at a very low voltage, having significantly low subthreshold swing with high on-off ratio. Here in figure 2, from the gate voltage versus drain current graph, we can see that subthreshold swing is the inverse of the slope of this curve, which cannot be smaller than 16 millivolt per decade with the existing oxide capacitance and substrate capacitance in series. It is theoretically demonstrated in figure 1 that a ferroelectric insulator such as aluminum hafnium oxide operating in the negative capacitance region could act as a step-up transformer of the surface potential in metal oxide semiconductor structure, opening a new way for the realization of transistors with stable subthreshold characteristics that is less than 16 millivolt per decade without changing the basic physics of the FET. Here in figure 3, we can see a NCFET along with its equivalent capacitance circuit. Adding a ferroelectric layer with capacitance in the gate stack in series with the oxide capacitance gives us the final SS. For a stable NC system, there should be no hysteresis in the system. In figure 4, we can see that addition of NC results in the subthreshold swings that is less than 16 millivolt per decade. For NC FinFET, the SS is lowered by 45% compared to the baseline device. However, the improvement in SS truly depends on the device design. For example, the use of a different Fe material can significantly affect the SS characteristics. Here is the structure of TFET incorporating ferroelectric oxide as the complementary gate dielectric operating in negative capacitance zone called the NCTFET as shown in figure 7. The developed analytical model demonstrates high on current and low gate at low gate voltage and exhibits lower subthreshold swing as shown in figure 8. While significant progress has been made in the basic understanding of ferroelectric negative capacitance in recent years, the development of practical devices has seen limited success so far. First, fabricating ultra-thin hafnium oxide-based ferroelectric films predominantly in the orthorhombic phases is still one of the biggest challenges for NC devices. Further, experiments on different ferroelectric or dielectric heterostructure capacitors have been going on to give us new insights into the domain structures, which strongly depends on the electrostatic boundary conditions. Finally, when considering the fabrication of NC transistors, more rigorous characterization methods are on process to provide convincing proofs of stabilized negative capacitance. Thank you, everyone.